Okay guys, today we're going to be talking about the depth first search. Now there are times that you're going to need to have a graph similar to this for whatever problems you're solving, and you're going to need to potentially visit every particular node in that graph. So we're going to talk about one approach to that, and then in the next class we're going to talk about another approach. So first off, let's talk about why maybe you would potentially need to visit every node in the graph. One possible way is you want to find a path from A to F. And you maybe want to find that in the quickest amount of time, or maybe there's some sort of cost that's related to each one of these edges, and you want to be able to figure out the best path to get there. So that's one. So the way to do that, we're going to talk about here with the depth first search. Another one is you may need to do something to every one of those nodes. So we may need to actually go and be able to process some data on every one of these items. Maybe it's setting a parameter or calling some sort of update or whatever it ends up being. There are times that you're going to find where you may need to do something. An example that you will see a lot is like coloring. So you may see something where you like color red, blue, and you want to have everything equally distributed. This is one way that you could actually operate this as well. So you can see over here on the right, I actually have a stack drawn. And we're going to talk about the differences between the depth first search and the breadth first search. And the big difference is the depth first search uses a stack. So let's jump right into an example. So in this one, we're going to start with node A. So we're going to say we visited node A. I'm going to just put a little bit of blue there, just so we can indicate that. And we're going to add A down here in the stack. So remember, a stack, we're like pushing things down on the top, and we're going to be popping things off from the top. So there's a couple different things that you may encounter in your career, especially when you're dealing with things like this. When you're dealing with a depth first search with no weighted edges, it doesn't really matter whether you go down the B or the S path correctly, or in whatever order. But if weight or some other type of parameter is a factor, sometimes you can vary that with other type of criteria. In this case, we're going to give you the example of we're just going to go down the B path. So we're going to push B on the stack, and we're just going to put a little bit of blue in there, and now we visited A and B. And really what this blue that I'm doing here is we're marking that node as having visited it, so that when we do the next route through, we're going to be checking to make sure that we haven't visited that node already. So B has nothing, right? So B in this example has no more edges. That is the end of that branch in the graph. So what we want to do now is we want to pop B off. So B has been removed. We have now gone back to A. We're going to look at the nodes that are attached to A that potentially have not been visited. So we're going to check B has been visited in this case. We're going to get to S, and S hasn't been visited. So we're going to mark it. We're going to write down S here. And then we're going to push S on the stack. Again, now S has C and G attached to it. The direction doesn't matter unless there's additional criteria. So in this case, let's just pick C. So we're going to actually push C onto the stack. And we're going to add C here. And we're going to mark that as visited. C now has a couple different nodes on it, 3 in fact. And we're going to do the same thing. So now we're going to push D here and mark it as visited. We get to D, there are no more branches. So what we're going to do is we're going to back up to C, and we're going to be popping D off the stack here. And we get back to C, and we're going to be looking at all the nodes to find any, if all of them have been visited, we're going to be backing up one. In this case, we actually have E. So we're going to be able to go to E here, mark that as visited. We're going to push that here on the stack. We're going to push that here. Now, in this case, E actually is attached to H. So we're actually going to push H on the stack. And we're going to push H on the stack here. And so these are the nodes that we visited already. Those that I'm keeping track of. So this would be like our output. You know, we get to a node, maybe we wanted to actually output all the different data from it. So we get to H, and H only has one as well. So we go here, and we're going to push G. And we're going to push G. Okay, so now G, the two nodes that are attached to G, so we're never going to want to come back from the node that we're coming from. But both of those have been visited. So we know now that we can pop G, go back to H. H again, all the nodes that are connected to it have already been visited, so we pop off H. We get to E, again, the two nodes that are attached to it have been visited, so we get rid of E. We get back to C, so we haven't added any more to the list, we're just literally popping data off and checking for new paths. We get to C here, and we check D, we check E, both visited, and we check F, so we're going to push F on the stack, and we're going to output it here, and mark it as visited. So now once we get to F, F has no more attachments to it that haven't been visited. We're going to pop it, we get to C, everything has been visited around C, and then we're going to go back to S, everything has been visited around S. We get back to the root node, there are no other branches on the root node, so our stack is empty. This is all the data, all the items in this graph we have now visited. Really, really helpful algorithm. Very easy to actually implement once you understand this idea. Stacks are really the key to it. So you're going to be pushing nodes and then also being able to change data on the node saying that you visited it. Those are the two major criteria here. Let's say that we've got the problem where we actually want to find the distance from A to F. And maybe each of these edges are actually weighted. Depth first search doesn't solve that for you correctly. What we're going to dig into in the next session is we're going to actually talk about the breadth first search, which will allow us to find the minimum distance. In a depth first search, it really works well primarily when you're doing unweighted edges. Now, there may be some type of criteria, and I have done this, and whether or not this is going to be valid for all your cases, where picking your node can be based on some sort of criteria leading to it. But typically, starting at the way that we did here, we're not going to be able to find the minimum path to the node. We will find a path, we just cannot be guaranteed that is the minimum path. Alright, so with that said, hopefully that gives you a pretty good introduction to depth first search. And in our next video, we're going to talk about breadth first search.